Alright, today we're going to talk about nucleophilic aromatic substitution by addition then elimination, and then the opposite, which is elimination then addition.
So first we'll be going over addition and then elimination. For an aromatic ring to be attacked by a nucleophile, there must be three conditions. These conditions are that the aromatic ring must be electron poor, the aromatic ring must bear a good leaving group, and the leaving group must be positioned ortho or para to the withdrawn group. So as you can see in this example here, this reaction does not work because only two of the three requirements are fulfilled. However, this is a much more appropriate reaction as all three of the requirements are filled. We will now show you a mechanism to show you the step-by-step process of this addition and then elimination. So first what's going to happen is we're going to take the OH group and it will attack right here. And once it does attack there, this pi bond right here is going to break and will deposit its electrons right there, creating a negative charge. So from this point, what we'll have now is a Meisenheimer complex, which is basically just a giant resonance structure. So we're going to have these electrons here, which is a negative charge. And at this point, these electrons are going to come down and form a pi bond right there. And once that happens, this pi bond is going to break and deposit its electrons right in this corner here where the nitrogen bond is with the ring. So we'll have our electrons here. Once we get to here, these electrons will come up and form a pi bond right here. And this pi bond will break and it will deposit its electrons right here, creating yet another negative charge. So we have this negative charge up here. So at this point, what's going to happen is that these electrons are going to come back and reform a pi bond down here. And once that happens, this pi bond is going to break and it's going to form a double bond with this nitrogen here. And lastly, what will happen is the double bond between this oxygen and the nitrogen, it's going to break and form a negative charge where this oxygen is here. So once this happens, the last step basically of this mechanism, the electrons from this oxygen are going to come up, form a double bond. This double bond between the nitrogen and the aromatic ring is going to break and come up and form a pi bond there. Once that happens, the pi bond here is going to break and form right up here to form another pi bond. And finally, this bromine is going to act as a leaving group and pop right off the structure. So that's basically the whole mechanism, and this is the NAS product from this mechanism.
Alex talked about addition then elimination, and now I'll talk about elimination then addition. With no strong electron withdrawing group on the aromatic ring, mild nucleophilic aromatic substitution conditions will not make a product. If you use harsh conditions like high temp, you will get a reaction to occur. I will show the mechanism later. For this reaction, the product mixture regioselectivity cannot be explained using an addition then elimination nucleophilic aromatic substitution mechanism. I will now show the mechanism for this slide and the previous slide. The chlorobenzene as the starting material, and you use OH as the base. So this will attack the alpha hydrogen, and that bond will move down to, so there'll be excess electrons on this carbon right here. And then after that, the next step, these electrons move up to make a triple bond, and in the process, this chlorine leaves. What's formed is the benzyne intermediate. The next step is to you use hydroxide once again, and it will attack the upper part of the triple bond, and then the bond will move down to that position. So it will be like that. Okay, and then the final step is to just do a proton transfer. So H2O will be used for that. It comes down and it attacks there and moves out like that. And then you'll get the phenol product. Okay, you start with the chlorobenzene as the starting material, and you're going to use NH2 to attack the alpha hydrogen, and the bond there will deposit its electrons on this position here. So you're going to have that, and then those will move there. Okay. From there, you're going to have electrons there, and to get to the final product, you move these electrons up to make a triple bond, and then this chlorine will leave in the process. So the final product is called benzyne. It'll be a triple bond here, like that. Okay. Using the benzyne from the previous example, you can attack it with NH2 in either this position or this position, and you're going to get the two products shown. And then you just use NH3 as the proton source. So in the first one, the electrons from the NH2 attack that side, and then this bond will move down to there. So in this, you're going to have the electrons here with a negative charge. And then to get to the final product, you attack the NH3 like that, and it's just like a normal proton protonating thing, and then that's actually good. So that's one thing, and like I said before, this is 50%. So it's 50-50 for both. Second way is to do a similar thing, except instead of attacking this this position, you attack that position. So those will attack there, and then these the triple bond will move up there, like that. So you're going to get electrons there, like that. And then like before, you just attack the hydrogen, and you'll get that product. And like I said before, this will also be 50%.